Well, thrilled to be here. A big fan of Materials Project. I think that that resource has done so much to make my job possible, right? Doing materials informatics, it relies so heavily on the data, and there's some great repositories, and Materials Project is just one of them. So really grateful to it, and I'm happy to now participate in this. So I want to get started. Today, as you mentioned, I'm going to be talking about generative models. So before I do that, I do want to recognize that, I don't do any of this work. I have the great pleasure of presenting it and telling you about it, but this is all done by these wonderful people and supported by these fantastic agencies, right? So from industry sponsors or federal agencies, we are grateful to them. And I want to point out these people, and I'll call individual people out when we get to their sections on sort of their contributions, but this is sort of a snapshot of most of the people in our group right now. There's also a lot of things that I'm not going to have time to cover in our talk today, but are things that we're really excited about in our group. For example, we've done some really, I think, great work on answering these questions about, can materials informatics or machine learning actually extrapolate to actually discover new materials? Can you build custom algorithms that do things that we need materials research algorithms to do, right? Where are you going to find data? Can you develop custom features? Actually, with Materials Project people, we published the best practices, which I think is sort of the definitive best practices guide for this field. So do check out some of this other stuff. But today I'm interested in materials discovery, right? And I love to start with this image, and maybe you've seen it before, but what do these things have in common is the question that I like to ask people, right? You see Play-Doh, you see vulcanized rubber, super glue, Viagra, all these things, like what do they have in common? They seem pretty random, and they're all materials. What they have in common is that all of these materials were discovered with some element of fortuity, right? Of chance, of luck, really. These were not like a rational design led, like now I'll add this amount and I should get this outcome. No, like these things were sort of an accident, a happy accident that led to the discovery of some really amazing and crucial materials, right? So in the first section of our talk, I'm going to be talking about materials discovery with the hypothesis that we're going to try and prove that, can materials informatics actually accelerate materials discovery? And I saw that Jacob Bergoch, my friend, spoke on your seminar a couple of weeks ago, so I'm not going to retread what he did. I'm just going to give a brief overview of it. From our group, the person our group working on this was Marcus Perry, but realized that this was done in conjunction with several other people, including Jacoba's group at University of Houston. But I like it as an example just to set the stage for the rest of today's talk. It's sort of a toy example for materials discovery. Maybe you recognize this. This machine is called Nanny. This is one of Elon Musk's toy projects. This is somewhere tunneling a freeway underneath Los Angeles right now, as far as I understand, right? And if you're going to be cutting through rock with one of these giant machines, the tip of it, I don't know if you can see these, but at the tip you have these sort of cutting inserts, and they have to be harder than the rock they're cutting. And finding these materials that are known as super hard materials that can cut through rock is sort of a challenge. Because if you look at the sort of hardest materials out there, the best ones, you've got diamond, but we're not going to take gemstone quality things. It would be too expensive, and there's better things to do with these, right? But diamond is a pretty amazing material. So what the folks have done over the years, about 70 years ago, actually discovered by this fellow, right? This guy right here, who grew up in my hometown, Tracy Hall, he grew up in Ogden, Utah. He was the one who actually was the first person to realize you can actually take little tiny bits of low quality diamond and compress them together if you have the right type of press. Fascinating backstory. Check out our podcast, episode 18, if you want to learn about it. But I think it's so rad because he went to GE. That was sort of his dream, was to work at General Electric. He goes there. He invents what's called the belt press, which is essentially like a uniaxial press with sort of a girder going around it so you could go to higher pressures. And he was able to make the first polycrystalline diamond. And he gets I seriously think it was $10, right? For this thing that has now gone on to be an incredibly lucrative technology. He got $10, and so he was feeling a bit jaded. So what's he do? He comes home to Utah. He goes to Brigham Young University, BYU, where he invents a better version of it. This press on the right, this is called a Bridgman anvil. It takes 6 sides. It sort of squeezes on it. It's a cubic anvil press. Anyways, making these things, a problem with making these diamonds is that it's high pressure and high temperature. You can see the size of this person next to this at US Synthetic just down the road in Provo, Utah. It is prohibitively expensive. You can't make pieces larger than about a hockey puck, and even those are really expensive. So we would love to find a new super hard material that is super hard but doesn't require such extreme pressures. Temperatures we can do, but pressures are what's really hard. So we decided to use this machine learning approach, and I'm going to go very quickly through it because you already saw it. Again, we started with data. Thank you, Materials Project. This was a snapshot as of a few years ago, right? I'm sure these numbers are all far larger now, but we looked at this and we said, oh, great. There's, a bunch of inorganic compounds, and, this subset of them, about 5,000, have elastic tensor, and that's what we need to make our predictions. So we look at those, we threw out the ones that were hypothetical structures, meaning we cross-listed against whether they had been experimentally made before. That's our data. Now, you know that in a machine learning approach, once you have your data, you need to featureize it because a machine learning algorithm doesn't know what AL203 is. That's just a string of characters, right? So you have to tell it what AL203 is or tell it what its structure is. And there's different ways to do this. In fact, gosh, that's somewhere where the most exciting work is happening right now is in this feature development space of materials informatics. So in our case, we did it strictly based off of the elements, right? We didn't give it the structure, just the composition. So we did a composition-based feature vector. Once you have that, you now have a way to represent your material. Then you need to find the patterns in your data between the input vector and your target property of interest. In our case, the shear modulus and the bulk modulus. And there's tons of tools for that, right? Neural nets get all the glory right now. Transformers actually get really a lot of the glory right now. But there's many other options. There's support vector machines. There's ensemble methods. All these different tools. They're all finding patterns, and they have sort of pros and cons in different ways. Once you've done that, you can now evaluate your materials, right? So we were able to do a cross-validation, make sure our models work. What you're seeing here is, the predicted value for, in this case, bulk modulus against the training set, the predicted value of shear modulus against the training set. And, a perfect model obviously would have this 45-degree line with all the points right on, and we don't have that. This isn't meant to be, for example, a replacement to DFT or something which would do better, but look at the sort of average error. If you look at the root mean square error on these, it's something like 15 gigapascals, which is incredible. If I took any expert in this field and I said, hey, given this formula, could you tell me the bulk and the shear modulus? And could you do it with a root mean square error of 15? No way, not even close. So this is a powerful tool for screening, right? So we used it to screen. We said, all right, now let's take these databases of materials that we know can be made. Let's throw out the things where they made them at high pressures. And so that left about 100,000 compounds in the Pearson database, which we were using. Of those 100,000, it included stuff that you couldn't predict even if you wanted to at DFT, or things that would be really hard, disordered structures, F electrons, ternaries, quaternaries for crying out loud. These would be really hard to predict, they'd be slow, and yet we were able to screen them doing a proxy calculation very quickly on just like a cheesy laptop, no supercomputer needed. And what you get is this. So now you have the predicted shear modulus, which is a measure of rigidity of your structure, against the predicted bulk modulus, which is a measure of incompressibility. We would expect to find super hard materials would be in the top right quadrant. That's where you expect high hardness, right? These two things, if you add some combination of them, you get hardness. And I didn't show the equation because I'm sure Jacoa did, right? And sure enough, we find our super hard materials there, but we also found a couple of new materials, right? This rhenium tungsten carbide system, moly tungsten borocarbide. We made these things. It wasn't too hard. All we had to do was arc melt them, no high pressure needed. We had to do it a few times to get the stoichiometry right and get them phase pure, but we did. And when we measured them, sure enough, we were able to find that at low loads, they crossed the threshold for being super hard materials. And these were at the time something like the 11th, hardest materials ever discovered, which is exciting because this project was about 6 months in. It took almost no time at all to do this. So this, I think, is a really good example of how machine learning can accelerate materials discovery. But, and there's a but coming, right? Was this really a discovery? Was this discovery? I would argue that this wasn't discovery. In fact, as we went out and gave this talk to people, we'd tell them about this, like, well, what materials have you discovered? And we're like, well, look at this moly tungsten borocarbide. And they're like, oh, so you're telling me a transition metal borocarbide is hard? Like, that's not very surprising. That's not very surprising, right? Plus they said, oh, and this material was known before. Somebody had made it. Just nobody had measured its hardness before. And this really gets to the heart of what my talk today is about. Yet there's a difference between screening and generating, right? So this is essentially what we did. We started with, we had these known compounds that came from our database. In this case, it was the Pearson, but it could be the Cambridge or whatever else, right? And these have unknown properties. They're missing a label. We don't know if they're good for something, but we can build a machine learning model that predicts that if you have data from literature, which gets informed by experiments, either computational or physical experiments. Then we end up with this ranked candidates, and we can do this loop over and over. And this is great for screening. So my gosh, I've seen so many talks now that show sort of the funnel where you have a bunch of candidates coming in, it passes through some sort of funnel, and out comes a down-selected group that might be good for what you're interested in. But it's screening, it's not discovery. Discovery would look different. Discovery would say, all right, instead of starting with a known database of materials that have been made before, let's start with chemical white space. Regions where we think you might have compounds that might exist, but nobody's ever made them. Those, obviously, since they're unknown compounds, they also have unknown properties. How could we find those and then tap that into the same sort of approach for machine learning prediction? That would be generative models, right? So with that introduction, let me dive into 3 examples. First, before I dive into my 3 examples, let me give you an example from images, because it's just a nice segue to what we ended up doing. So to answer the question, can machine learning generate something entirely new? Let's turn to the field of image for a moment, right? there's this article from 2018 in the New York Times where they were talking about these generative algorithms for making faces, right? And they're trying to trick you here. They're saying, which one of these two faces was, an actual photograph of a human, which one's fake? And they're both fake, right? And that's pretty surprising because you look at these and these look like they could be real people. And this was with 2018 technology. Holy smokes, have we come a long ways, right? This is based off of GANs. GANs are generative adversarial networks. I'm guessing most people on this call have heard of them, but if you haven't, briefly, I'll say that you have two different neural networks, a generator and a discriminator, that compete with one another. The generator takes random noise and tries to make something that looks like a face. Meanwhile, the discriminator has some combination of real faces and fake ones, and it tries to tell the real from the fake. And the key thing, and what's not drawn in this diagram here, is that you tie these two things together. The loss function of these is tied together. So the better and better the discriminator gets at its job, which is the easier job by far, right? Discriminating real from fake is definitely easier than generating. But the better it gets, the better the generator has to get at making fakes, okay? This was the principle invented by who? Ian Goodfellow, a graduate student at either, I can't remember if it was Toronto or Montreal, but this Canadian grad student in 2014 invents this. And the first ones were not amazing. By the way, he's since gone on to work for Apple and Google and DeepMind, I think. He's a couple different places. But you can see the progression of this technology from 2015, 16, 17. They're looking pretty good. 2018, this was with StyleGAN, I think. It's looking quite good. Now you're getting high resolution. It's generating this. Like, this person doesn't exist in real life, but glancing at it, you could be like, yeah, that could be a real person, right? That looks like it's generated something quite new. By the way, this has come a long ways now. StyleGAN was good, but one of the problems StyleGAN had is that as you take this image and you put it in the latent space, allowing the face to sort of move, you've seen these deep fakes where you can make people talk and do that. One of the problems they ran into is like these minor textures, like the dimples on the pores on the skin, or like the little textures of the hair. They were doing what's called texture sticking, where they would sort of hover, the face would move underneath it, but they would sort of hover and it didn't look quite right. This has been fixed with, I guess it's now 8 months old, I think it is, Alias GAN, came out of NVIDIA. Amazing, just absolutely remarkable what's coming out of it now. And it's doing other really cool things, right? Style transfer has now become possible using GANs. The idea behind style transfer is you take your generative adversarial network, but when you're feeding your images, like if I go back to our images, what if the only type of real images you gave it had a certain style to them, right? Well, then your generator would start to learn things that look like that style. So the idea behind a style transfer is you do that with your generator, then you freeze the weights, and then you input something like your real image, like me or my adorable daughter over here, and you send it through these pre-trained but frozen networks, and they will modify the input to do different things. So you can have, like, I don't know, that's king, that's like happy person, there's like baby, like it does these transformations which are pretty slick. That's style transfer, which again, I think you could think of as a type of generative machine learning, okay? And they've done this obviously beyond just faces. You can look at landscapes. This is not the Alps. This is a GAN version of the Alps. It invented this. It's not real, but boy, it looks like it, right? And then one last thing before I get into our research, I just want to plug my student Ryan Murdoch did some incredible stuff. He's now working for Adobe doing even more of this. But here's a Digital Trends article where they interviewed him and talk about the tool that he built. It's called Big Sleep. And like the name here suggests, like the headline says, it's like a Google image search, but for pictures that don't yet exist. So you provide a text. This time in Google, you provide a text query, but here it's a text prompt. And in Google Image, it searches the web for images that match that query. But here, it creates the image to match your prompt. So for example, this funky one in the middle here, the text prompt was an intricate drawing of eternity, and voila, it spits this out, and holy smokes, right? Here's a bunch of other ones, right? A strange ghostly figure in the forest. Right? Amazing. How about this one? Hungry dogs will devour in the daytime. It does some incredible stuff. So GAN generated art is becoming a pretty cool field. And anyways, I think it's a really compelling example of, yeah, ML can be generative. We can go beyond just our training set to go beyond screening to actually start generating things. So let me give you an example. First, let's start with style transfer. Is it actually generative, or is it more sort of just inverse design? We're nitpicking, but regardless, I'm going to show you an example of how we use style transfer for, let's call it inverse design then. This work was really led by Andrew Falkowski, which if you listen to the podcast, my materialism podcast, you'll know that he's the co-host, a wonderful student. He's a great grad student as well, and a really bright guy. So he led this work with help of my former grad student who's now working at Verana Health, I think it is, doing data science for them, Kai Kawe. So What is style transfer? I've already showed you. Again, you take some sort of input, you train a bunch of images of a certain style, and then your input now gets adapted to that style. So for example, here you see, I forget the name of this place in Tübingen, Germany, Necker something, whatever it is. And you have Edward Munch's the Schrei, right? The scream, and you've now adapted this to take that on, right? So how does this actually work? It uses convolutional neural networks. Convolutional neural networks, if you're familiar with them, you start out with your image and it goes through a series of convolutions with specific filters. The filters are actually learned. These filters allow you to abstract portions of your image. I could go on and on for a whole hour about CNNs and we don't have time, but I'll just say that these filters start out with a very weak abstraction, so it might find edges or colors or gradients. And then as you convolve those after pooling operations to downsize it a little bit, you start to abstract it to the point where you can find textures, you can find really interesting things. So they use that, and with these filters, they were able to extract the style of different images, right? These styles sort of emerge. And from the end of the convolution layer, where the pooling is done, you get the most important components, and this is your content. So you have this sort of way to parse out style from content, right? At least in the original paper where they introduced this. So their goal was then to say, all right, now let's take that pre-trained network, freeze it for a moment, and send through white noise. As you send through the white noise, you will create this, there's a word for it. It's not a filter, it's the output of the filter. It's like a preferred input, I suppose, is what you'd say, right? For both style and content. So then when you feed your actual image through that you want to stylize, you're just minimizing the difference between the style preferred inputs and your content preferred input coming from the actual image, right? That's the idea behind style transfer in any case. So how could you potentially use this to materials informatics? How could you style something to have a certain style based off the types of materials it was trained on? Well, consider this example. And first I'm going to say that transformer models like CrabNet is where we decided to use this because we made CrabNet. We're big fans of it. But they're also, they work well for it. They're a powerful representation and they adapt well to style transfer. Here's how it works. You take your input vector, right? Again, the string AL203, the algorithm doesn't know what that is, but we can turn that into a vector of numbers that it can use that represents that material, right? You can do it on a one-hot encoding, a fractional encoding. You could give it composition-based information. In CrabNet, we do both element and fractional encoding, and then we create this so-called element-derived matrix. If you want to read more about it, this paper is in NPJ Computational Materials. I'm happy to tell you all about it. But the details of here of how you do this element-derived matrix involves the components that you'd expect to find in an attention network, meaning it has a query key and value system for all of these individual elemental elements, the components of our composition-based feature vector, right? They have to learn their interaction with one another and all other components. And you do that using a query key and value system, which is at the heart of all multi-hit attention networks that are revolutionizing data science right now. So we applied this to materials, right? Right now, there's no style transfer happening. All we have is an attention block, which allows us to learn what does aluminum pay attention to. Of all the other elements, how much does aluminum pay attention to all of them for predicting some sort of property? That's what this does for all the elements, right? And if you look at the sort of outputs of these, like what it's actually learning, you can see that it does do a good job of finding and memorizing this implicit representation of chemical space. So here you're seeing portions of our element-derived metrics against one another. Or sorry, this is different elements where you're showing how they're correlated one with another using these attention maps. And you can see that, yeah, it finds different groups of materials. Like the elemental trends in the periodic table are all present here for the most part, okay? So to make this amenable to style transfer, what we need to do is then compute a gradient based off the output of what something was created. We're now going to tune the input. This is a big difference, right? This is moving to generative. It's not screening, because instead of just having a predefined list of materials that we're going to send through where they all can calculate their feature vector using the same tools that everyone's been using, we're now going to generate these vectors on the fly in order to achieve some sort of outcome. So for example, let's say you trained a neural network to predict a bulk modulus. Well, then you pre-train it, and now you have a loss function that says when you predict something, look at the predicted value of bulk modulus compared to, say, infinity, and try and minimize that distance. That's where the gradient comes from that allows us to tweak these values in this style transfer approach. So in other words, you have your fractional vector representing your material. We'll call that little f here. We're going to turn that into a featurized composition using the multi-head attention. So we send it through our element-derived matrix with that individual feature. Now, using that element-derived matrix in some sort of function, in our case, CrabNet, you could train it to predict some property. Y or Z might be two different properties. Maybe you want to predict something that's both a really high thermal conductor and a really low, I don't know, density, right? You could define these things. You could have multiple multi-objective optimization where now your total custom loss function takes into account how well does it do at predicting bulk modulus or thermal conductivity, how well does it do at doing some other thing, and you can scale these things differently. If it's more important for you to find materials that are high bulk modulus, you don't really care that much about density, but it's a consideration, well then you can tune these things, right? Alpha and beta are tunable. Like you can make this custom loss function be whatever you want to do multi-objective optimization here, right? So here's how we've done with it. Like this is an example, right? You can see that the algorithm, here you're looking at the loss versus training epochs, right? The algorithm is pretty effective at dropping out unnecessary elements when it has the task of improving some sort of property. Like for example here, we started out saying you can use titanium, cadmium, or carbon, and you're trying to maximize, in this case, what is it, bulk modulus, right? So after a couple of epochs, it's realizing, man, when I get rid of cadmium, it just makes it better. And then it tries it, maybe I ought to include it. No, I ought to just get rid of it and just not have it. And finally, this thing settles pretty close to the stoichiometric amount that you'd expect for titanium carbide. So it's learned that that's a harder material, given the options to explore that input vector, right? Here's another one. Here's two different properties. Here we're saying to maximize both bulk modulus and I think it's minimize your decomposition energy, right? And you can see that, again, as the epochs change, it's learning. At first, it's doing a bad job of maximizing modulus. So it turns around and it learns that, here's the right way to do it, while more or less minimizing your decomposition energy. And you can see what that's doing in terms of composition. It started out adding calcium, and it's like, no, that's making it worse. And it learns to slowly turn that calcium off. So this is, I think, I think it's fair to say that this is somewhat generative. We're generating new compositions in this way, okay? Here's another one where it's capable of filtering out non-essential elements if you give it a bunch of elements. So in this case, right, you don't always know exactly which 3 elements to start with. So maybe give it a whole bunch. It can learn to turn off a bunch of these things and just keep a few, right, which is pretty slick. Okay, this paper's been published. It's in IMMI, a great journal, Integrating Materials and Manufacturing Innovation. I think more people ought to publish there. It's a TMS Professional Society journal, so check it out for what it's worth. That's where you can find this paper. Now, when this was published, we were pretty happy with it, but we've done more since then, right? Because everything you saw right now was relying on gradient optimization. We had our loss function, we calculated a gradient. Through backpropagation, we could change this input vector to slowly nudge things. That's only one way to pick your input vector. There are many other optimization tools for doing that. And I was sort of naive to this, and I thought gradient optimization was just like the bee's knees, and I just used it all the time. But I'm increasingly seeing the potential value in doing what's called black box optimization. One of the big advantages of black box optimization is like, here, look at your gradient. As long as you can tell the gradient, it will move down the gradient. But then when you get here, depending on the step size and your details of your optimization package, it might never get out of this local minimum because it says, oop, I'm going uphill. Either way, this must be the best. But we know, if you actually had a picture of the lost landscape, that there's a better solution out there. One of the things that black box optimization can do fairly well is escape these local minima. So generative, genetic algorithms are a good example of this, but there's others, right? Well, let's take a look at this. Here you see dominance theory. Dominance theory says, let's say you've got 2 properties you care about. There exists a bunch of these non-dominated solutions, meaning all these data points are the best if you're trying to, let's say, minimize decomposition energy while maximizing electrical conductivity. They're non-dominated solutions, meaning you can't, there's no way that I could lower my decomposition energy at this point without also lowering electrical conductivity, right? Sometimes this is called a Pareto front, right? These non-dominated, these solutions, right? So if you look at what a genetic algorithm might be able to do, is it might say, fine, this is like our current Pareto front, but maybe there's a bunch of other rejected materials, and if we combine these things together, through different mutations in the details of this, there's many different ones. There's vanilla genetic algorithms you can use. We actually built our own tools for this, and the paper is forthcoming. Watch archive. It should be showing up in the next week or two. But we did our own version of this to basically try and find the best new non-dominated solutions by combining interesting combinations of elements and ratios of elements, right? So what you end up with now is, let's say you're looking at thermal conductivity as a function of decomposition and enthalpy, right? Here's your non-dominated compositions, right? Okay. That's the Pareto front of the sort of best, most interesting materials there, okay? Well, if you do genetic algorithms versus the sort of style transfer approach that I showed you previously, you'd see that the genetic algorithm, it beats it, but it does so by using crazy stuff like platinum, actin. Like, this is nuts. Like, these materials are probably the ones that are not of real interest because you're never going to work with them, or maybe, anyways, you're dubious of those. So you can modify this a little bit. You can start to throw out, you can do exclusion of these exotic elements or structures or whatever else you wanted to. But the point here is that when you do that, you start getting some interesting materials that might look, yeah, maybe that's worth sort of looking at for whatever your application may be where you care about this. And then you compare that with the gradient-based optimization, and it seems to do a better job of reaching out, right? Of getting out of these locally pits of local loss, right? And obviously as the number of objectives increases, as you're doing multiple different parameters, this gradient-based methods do even worse. They really do fail to explore. If you look at what they're predicting, it's really all in the same family, whereas genetic approaches seem to do a lot better. And so we've been increasingly looking at a lot of different genetic algorithms and actually developing a few of our own. Anyway, so more on that in another day. So I think I've hopefully made the case that style transfer is maybe one way to think about generating materials, right? Moving to generative models. Now let's switch gears. This work is primarily by Michael Alverson, who I see is on the call. Michael, good to have you here. He was working at Google most recently, and now he's doing his grad degree at USC, but he was an undergrad in our group doing phenomenal work, as good as any of my grad students, right? And he started to get some help from Zara Gholami, one of my new grad students as well, working on this topic. And the task here is, all right, for a generative model, what if we could just generate the sieve card directly? Now, why am I excited about that? If you look at the field of chemistry, our friends in chemistry are doing some rad stuff with generative models, but the but here is that they kind of have an easier problem because a lot of the molecules that they create, they don't worry about how those crystallize, right? They just say it's a standalone molecule, which means you can just add on functional groups willy-nilly wherever you want. You don't have to worry about the symmetry constraints of how this thing would crystallize into periodic matter. Those of you that have worked on representations of materials for materials informatics, you're aware of this, that this periodicity requirement of inorganic materials is a real bugger. We don't have a great solution to it. Our solution that we proposed here, and we were pretty skeptical this was actually going to work, was we said, well, if you have the sieve card, then it will for sure obey symmetry, right? If you could just generate the stuff in the sieve card. So what's in the sieve card? Like if you've opened a sieve card, I'm guessing most people on this call have, but you know that it has things like ABC, your lattice parameters. It has alpha, beta, gamma, the angles between them. It has the space group number, right? Which tells you all the symmetry operations to use are based off of that one number. And then the basis. The basis tells you what atoms and where are they, and their occupancy, thermal parameters, stuff like that. If you could predict this stuff, which isn't that much, what is that, like 10, 12 different things? Potentially more if it's a really complicated structure, but like it's possibly doable. And if you have this, it will for sure obey symmetry, okay? So that was the proposal here, right? So to do this, we used GANs. GANs are powerful. They're really good at generating new things. They have their downsides, and there's also competing technologies. There's reinforcement learning and variational autoencoders. There's other things out there, but GANs are what we started with. The idea here, just like you saw before, you're going to have a generator, which is going to take chemical white space, right? You give it open possibilities. You don't restrict it. This generator is now going to spit out fake unknown compounds, right? And then you can take those fake unknown compounds and you can compare those with real known compounds, and your discriminator is going to have to try and pick which one's real and which one's fake. And that loss function, just like with any GAN, is going to tie these two things together. Now, we are interested in adding an additional step here. We would like to actually calculate distance from the convex hull using a really fast calculation, not with DFT, with a machine learning. Like there's already been several papers showing that you can do a pretty good job, not perfect, but a pretty good job of predicting distance from the convex hull with a machine learning model if you have the sieve card. Well, this generates sieve cards, so you can run them through there and toss out the fake and likely unstable compounds. This does a good job of sending less garbage to the discriminator if you add this stuff in here. So the discriminator gets more things that look real, and because you're throwing out a bunch of the nonsense ones. Okay. Now that was the idea behind this, and thank you to the people, Materials Project. I'm seeing the people in this call are created the tools that make this possible. So big props to PyMat Gen. It makes it really easy to extract all this information we need, the ABCs, the alpha, beta, gammas, all this jazz, and the basis. We can pull that out really easily with these tools. The data you can find in lots of places. We were looking at the PCD because that's what we have. We like it. It had about 300,000 sieve cards. Interestingly, only about half of those could be used because, this was a surprise to me, but many of those cards only have the space group information and maybe the unit cell dimensions, but solving for the individual atomic positions is a harder thing to do, and those are not always reported. So we had to throw out them, but still, we were left with a huge number of real materials, 143,000. So plenty to train from for our generator to have lots of ideas of what a real material looks like when it creates them. So now, how do you represent it? Like, what does the actual generator use, right, to generate something? What is the input, and what does it actually try and output? Well, you have to represent your material, and you could do that in a bunch of different ways. Here's how we decided to do it. Ignore the fact that there are 7 rows for a moment and just look at the top row. You've got your ABC. We know we have to have those. Alpha, beta, gamma. This is all your structural information. Tells you the size of the unit cell and the dimensions of it. You have to have the space group because, again, from that comes all the symmetry operations and all that. Then you have to have you have to have entries for your different atoms in your basis with their according positions and fractional occupancies and all that stuff, right? Now the catch is that some crystal structures like silicon, right? Silicon in the diamond cubic structure, you need 1 atom to define that structure. That entire structure, it can be periodic out to billions of atoms, is defined by a single position in your basis, right? But other ones might have many, dozens or even hundreds of atoms in the basis. So we had to make sure that this representation, this matrix, was large enough for the largest one that we would ever see or want to be able to see. Or we had to throw out things that were larger than it and not train off of them. So in our case, we accepted up to 200 unique atoms in the basis, right? Now, why are there 7 rows? We did that because averaging these predictions over 7 made it much more stable. Now, why 7 and not 11 or 12 or whatever? You'd have to ask Michael, who's on the call. I don't know. I think that's the one we tried and it seemed to work pretty well. But essentially, when you predict things, instead of just using ABC for these values, if you average them 7 times, it tended to be much more stable, right? Now, there are some constraints that we had to put on this. We couldn't do this completely unconstrained. For example, if the space group is over 195, we know with our domain knowledge that that's a cubic structure. Therefore, alpha, beta, gamma have to be 90, A, B, C have to be equal to one another. But what's interesting is that it sort of learned these trends on its own. We would nudge it, right? If they were different, we would average them to their average value, but we didn't have to nudge it very much. It was sort of interesting. If you look at how much it was happening, it was learning these trends on its own. And the same thing for all the different space groups. We did have to do a little bit of nudging to make sure that we weren't breaking symmetry rules, okay? Now, the other problem we ran into is that if you look at Pauling's rules for materials, there's a bunch of them, but the last one is parsimony, right? His 5th rule is parsimony, which says on average, most materials don't tend to have a whole bunch of different elements. They tend to be simple. They tend to have few different elements. There's exceptions to this, but if you think about it, think of how many binaries, ternaries there are. Now compare that with how many compounds have 10 different elements. It's staggering how much simplicity does seem to play a role. Well, one of the problems here is that the generator has 200 options for putting 200 atoms in the basis, and it might choose to put different atoms all over the place. And even more problematic is that it's using a regression. So it will predict that the material has the atomic number. The atom in this basis position has 13.44. Well, that doesn't mean anything. Atomic numbers are integers, right? So you could round it. I guess that would be one approach, but that doesn't fix the parsimony problem that it's predicted, 15 different materials here. So we tried a couple different things here. One thing we tried is k-means clustering, right? There's lots of different clustering algorithms, but if you just did k-means for a moment with k of 2 or 3 or 4, then you could force it to create a binary, force it to create a ternary, things like that, right? And then you can round these things to the nearest number. So this will force you to reduce the amount of elements that it's outputting to more reasonable values, right? So this is another hand constraint that we're tweaking this, right? We're not totally just letting this thing go on its own, but it made it a lot better. That said, on day 1, I remember these first GANs, when the GAN was working, he would create these civ cards, and the first couple that he sent to me, I was ready to be like, oh, stop. This is just embarrassing. We were not going to, my goal was here is like, maybe we could actually one day make a material that fools our chemist friends. But the initial output, it's like a gumball machine. It's just out of control. This was not going to fool anybody. It was diverging. It was really bad. So thankfully, Michael insisted that we keep on trying on this. And I was like, yeah, all right, let's keep trying a little more. He started changing it from just a sort of vanilla GAN with had convolutions and normalization, no normalizations. He started adding batch normalization. He started, I think, eventually adding different layers like LSTM layers. And you started to see sort of some improvement, but I was still not very impressed. And one of the real problems that we were running into with all of these basic GANs that we were trying is the loss function. If you look at the discriminator's job, it predicts real versus fake by taking the output of its neural network, and if it's a really negative number, then that through the sigmoid that you run it through says that's a 0, right? Negative numbers end up looking like 0, so you say fake, right? Whereas big positive numbers look like 1, and so you say real. This is how it does its binary classification, is through, it's kind of looks like a logistic regression actually, right? It's doing 0 or 1 based off of that, because it's hard to land somewhere in the middle. Not many entries are going to do that. The problem, though, is that as you become increasingly sure that it's a real material, so like a big positive number, the slope of this region also decreases. This is called the diminishing gradient problem, right? Or in other words, think of it like you're running a marathon. Like what if while you were running a marathon, the closer you got to the finish line, the slower you started moving. Because this gradient is what we use in backpropagation to tell the generator what it should do differently so it can do a better job of making new materials. And this is just an inherent problem with this type of loss function. Well, fortunately, there's other types of GANs out there. For example, the Wasserstein GAN, which does things differently. And if you're not familiar with the Earth mover's distance, which is the basis of Wasserstein GAN, the main point that I need you to understand for this talk is that it has a linear activation here, right? So that no matter where you're at in the prediction, you can provide actionable information to the generator. This is important because now our generator, even as we get better and better and starting to look at things like maybe start to look kind of okay, we can continue to improve, right? We don't suffer from this diminishing gradient zone, right? Now there's other things that he had to mess with, different ways to deal with the Lipschitz continuity, different approaches to normalization, and honestly, I don't remember what those were, but we could tell you all about them if you're interested. But in the end, we end up with things that we're not there yet, but we're getting closer to being to where we could fool our chemist friends. What you see here are 8 different materials, showing a couple different projections of each. And the task here is to figure out which one of these, we have 4 fake and 4 real. And I think that you could probably catch some of them, but I think that we'd fool some of you as well, right? So the green ones here are all fake materials, and we're getting better at making things that are starting to look realer and realer as we improve our GAN, right? So way more work coming on that soon. One of the big problems with this, if I told you what these elements were made of, or if I showed you like the average bond distances compared to other things of the same chemistry, then you would right away say like, oh, it's easy to throw them out. So we are fixing that problem next. The generating a sieve card approach has been phenomenal in that it allows us to generate periodic ordered materials, inorganic materials, but there's no chemistry encoded in here. At no point do we tell it that an average bond distance of carbon and nitrogen is 1.4 angstroms or whatever it is, right? So that's what we're adding now is we're going back to our representation of our material and we're adding channels. And the channels allows us to encode for each atom in the basis what interactions ought to be from all sorts of other materials. We think that that'll improve the types of chemistries that get reported so that we can keep the symmetry benefits here but start making chemically relevant materials that make a lot more sense. All right, the last section of my talk, in the time that I've got left, I want to talk about how we can go beyond generating just materials to generating interesting materials, right? So the GAN's job is to find something that looks like a real material. One of the problems, especially with GANs, is that they are really good at sampling from the center of a distribution. They do a bad job of sampling from the tails. But tails might be where the interesting materials are at. You might find a material that, yeah, it's a real material, but it's unusual. It's unlike other ones. It's atypical. It might have the properties you care about. So how do we make our generative models start to pay attention to interesting materials? This work is led by a current PhD student in my group, Sterling Baird. I think he's on the call as well. And Tran Diep, I don't know if she's on the call. She was an undergrad from Brigham Young University who joined us for the summer as part of our Reuse REU program here at the University of Utah. And so they've created what we're going to call the Discover algorithm. And Sterling likes to show this picture, and I like it too. It starts with this idea that when we're looking for new materials, we're oftentimes looking in the wrong spot. If you look at this cartoon, the cop says, oh, is this where you lost your wallet? He's like, well, no, I lost it in the park, but this is where the light is. How often do we do this? When it comes for a new material for whatever application, I think that we tend to say, well, these are the materials that people have looked at before, so let's just do a minor tweak on those, or these ones I know how to make, or something like that. We really limit where we ought to be looking because it's just dangerous and hard to look for materials way out in the middle of nowhere, right? So we'd like to find a tool that helps us do that better, right? All right. In this talk, I've already told you that the way that we represent things for machine learning and materials informatics is we start with a formula and we turn that into a vector, and there's lots of different ways to do that. Maybe you have the structure information, maybe you don't, but that's associated with a target. So let's go ahead and split this up into our training and validation data for a moment, okay? Then what we need to do is figure out in all the materials that we have, how similar are they to one another? Now, we can't take credit for this. This came out of Matt Rosinski's group at the University of Liverpool, where I will be for the next year on a sabbatical, actually working with them more on this. They built what's called the element mover's distance. The element mover's distance is really cool. It mimics intuition about chemical similarity. The idea behind it is it uses the earth mover's distance, which was the basis of the high-performing Wasserstein GAN that you saw us just present. And it basically says, like in a nutshell, it says if you've got 2 different distributions, how could you make the 2 distributions look the same? Well, the distributions are chemical vectors. So if you have 2 vectors representing 2 different chemicals, how do you make them look the same? What's the minimum amount of work, right? if you change them component by component, how could you make them look like one another? Hence the earth mover's distance. Like if you took two piles of dirt, how could you shovel the smallest amount of dirt to make these two piles look identical? That's what this is doing, but on an element basis. So it's using chemical similarity to do that, like the Pettifor scale, right? Which is a better way of organizing the periodic table than just the Mendeleev number if you're thinking about chemical similarity tied to its atomic number. Okay, so this allows you to create this matrix of similarity. The matrix of similarity, once you have that allows you to now do some really cool things. Like you can then say, well, let's do an embedding. An embedding is when you take something high dimensional, like our composition-based feature vector might have, several hundred components to that vector. Well, we can flatten that down to a much smaller space, like 2 dimensions or something else, but we can do it in a way that is aware of the similarities of these different materials, right? So we're calling this a density aware embedding, right? So, and there's tools out there. We didn't create this dense map and there's others, right? These are density aware embeddings that can reduce the dimensionality by taking into account similarity and density of these different points, right? And then once you've done that, once you've got a density aware embedding, well, then there's other tools like HDB scan that can actually produce clusters in this embedded space and say, all right, here's your different clusters of materials. So here's, I don't know, this is like 24 different families of materials as an output of this. So this is a different tool than we had. This isn't just like clustering. This isn't TSNE or UMAP, because this is taking into account chemical similarity in a way that hasn't been able to be done before. Why do we care about all of this? Well, the point is you could now pair this sort of analysis with your machine learning models that predict things or generate things or both, right? For example, let's say I have a model that can predict something like a bulk modulus or whatever else, right? But now you have a tool for measuring chemical uniqueness. So you have a new Pareto front. This new series of non-dominated solutions, you could look at materials that, look, they're great, but they're not very unique. They're right around a bunch of other materials that are just like them. So think of like a perovskite, where technically, yeah, if you tilt it slightly differently or swap out one little element and some fractional amount, it's technically different than the other perovskites that we know and love, but it's not very interesting. It's just a slight relative to them. Whereas another material might be lower prediction. It's probably not as good for the maybe property, but it's a heck of a lot more interesting because it's coming from a portion of our plot which no one had looked at before, right? So this is a new approach. This allows us to look at chemical similarity in a way that we've never been able to do before. If you were to partner this with our generative adversarial networks or our CrabNet for predicting properties, all of a sudden you have a tool for making generative predictions, but doing so for interesting new materials in addition to those that are just high performing that are sort of well known. So what's cool about this is obviously when you make your prediction, you don't have to care about just one or the other. You can scale it however you want. Maybe your prediction, you really want to care about the target. Like you want performance to be awesome. Maybe you're gonna, in another scenario, you really want interesting new materials. Like you're more interested in discovery than optimization, right? Well, great. You can tune these things with different weighted values of this new loss function that we're using here, right? So let me summarize in one table here. I know tables on presentations, but bear with me. The Discover algorithm, we're calling it, right? The Discover algorithm really connects powerful and recent tools for chemical uniqueness proxies in different ways. First off, it uses CrabNet, which is our tool for composition-based property regression. It's killer. It's a great tool. In fact, we just made it better. A paper just yesterday hit the archive where Sterling found a way to make it better using Bayesian optimization, using Facebook's new Bayesian tools for the hyperparameter selection. So check that out on archive if you want. But that predicts the properties for performance, right? You've got LMD. That's our composition-based distance metric. This supplies the distance matrix to DenseMap. DenseMap makes our density-aware dimensionality reduction. This allows us to obtain densities for the density proxy, meaning how unique is it. HDB scan clusters things, so now we can do chemically homogeneous clustering. Then you can come up with these different proxy scores for whatever you want to do. If maybe you want to weight it on performance, or maybe you want to weight it on uniqueness, this allows us to do it. And a Pareto front allows us to optimize in the presence of a trade-off scenario like we're now going to have. So how does it actually work, and does it actually work? We're nearing-ish the end of my time, so just got one or two more slides. Let me show you this. Does the Discover algorithm, I'm forgetting what it stands for, descending, stochastic, clustering, variance regression or something, right? How does this actually work for what we're trying to do? Let's take a scenario. Let's look at bulk modulus. If you look at the histogram of bulk modulus in some data set, I think this is actually materials project data, it's a log normal distribution where the vast majority are about 100 bulk GPA for bulk modulus, and a very, very small number, the top 1 or 2%, are maybe above 300, but they're not common. So what if you hid those? We're going to put those in our validation set. So the training set never sees a high value, right? the training sees normal values. If you've seen our extrapolation paper, we did something similar there, right? So with the Discover algorithm, can it train off of this training, and can we adaptively hope that it will learn some of these high-performing materials? That's the challenge here. So, okay, we're going to do this with an adaptive design technique. Adaptive design says, let your algorithm train, but let it keep on trying things, learning from what it learned in the past. So this is a Bayesian approach, right? Where we're now going to have a candidate pool. I think we started with 100 training points only, and we're going to give it 900 adaptive design iterations. The process looks like this. You're going to retrain CrabNet with these new points that you have. You're going to do the LMD, dense map, and HDB stuff that allows you to look at chemical uniqueness, compute your proxy scores. And again, you could weight this to say, I really want performance, or I really want uniqueness, or I want a little bit of both. And then you're going to have your ranked candidates. And you do this 900 times. Okay. So how do you know if you've been successful? Well, there's different metrics you could come up with, and maybe people on this call would have other good ideas. But one thing you could do is you could say, okay, of those top performers, the top 2%, how many of those, which it never saw when it was training, how many of those will it find on its own, right? That'd be one way to do it. Another one would say, okay, based off of the initial atoms it had, one for uniqueness might be how many new unique atoms get added. Or maybe how about this one? How many new unique chemical formulas get added that it didn't see before? Like those might be 3 different metrics, but you could probably come up with other ones. Our paper has a whole bunch you can take a look at. I'm just going to show those 3 for today. And then the types of algorithm that you choose, well, using the same framework, you could come up with different sort of approaches. One, you could just search at random. That's not going to be very good, but it's a good baseline. Then you could have 3 using the approach that I've described, the Discover algorithm. 1 using an emphasis on novelty. So turn your performance down to 0, meaning I don't care how it performs, just give me new materials. 1 where it's 50-50, and 1 where it focuses on performance, but we don't care about novelty. Here's the output of that. And I think it's just about my last slide. Here you see the cumulative on the y-axis on this top row. The y-axis represents your cumulative extraordinary, right? So how many of these extraordinary materials does it find? If you do random, it doesn't do a good job of finding them, right? And the novelty design doesn't do a good job of finding them. But the one where it's 50-50 or performance focused, it does a great job of finding some larger cumulative fraction of those interesting materials, which is rad. If you look at unique atoms, random does a great job, right? If you just pick an atom from a hat, it'll do a good job of finding new unique atoms. Novelty does the same thing. Exploration does a good job there of doing it if you focus on a 50-50. Whereas if you focus on performance, it's going to say, hey, I never need to use plutonium, right? Because it's just bad for this property, right? So it will actually do worse. Same thing with chemical unique templates, right? So you see the same sort of trade-off there. So we think this is a really cool tool. I'm a big fan of it. We want you all to know about it, right? Which is why I'm talking about it today. You can check out the Discover algorithm by going to Discover. You can go to take a screenshot right here, take a picture of this with your phone. It'll take you right to the read to the docs. This is all pip installable or conda installable. We've tried to make this as easy as possible for people to use this. So install it and use it. You can use it with custom data sets. You can get started with just a few lines of code. Even though it uses a bunch of these state-of-the-art other tools out there, we've made it really simple to just do this with a couple lines of code. You can make some really sweet interactive visualizations. It introduces the Discover and the Adapt classes in Python. And then there's continuous integration. You know, if you've got a question on this, we're really responsive. We're happy to help you out. So anyways, I think we're out of time, and I'm very happy to take some questions. So let me end by saying, first off, in 2 weeks, actually I think it's like a week now, 10 days away, the AIM conference is happening in Pittsburgh. I'm the chair of that, so I have to promote it. If you haven't registered and you're interested in some of the stuff I've talked about and you're near Pittsburgh, well, I hope that you're going to stop by. It's going to be a rad conference focusing on materials informatics, right? This machine learning in the material space. And then secondly, if I haven't promoted enough, we think we've got a really cool podcast. Check it out. It's Materialism. And with that, I'll take any questions.
Wonderful. Thank you, Taylor, for the really informative talk. Thank you to everyone that submitted questions via the Q&A panel. Taylor, I don't know if you can see, but the Q&A panel now has 17 questions on it. Yeah. If you'd like, you can maybe just read through those, and we'll try and mark the ones that have been answered. Feel free to go in whatever order you like.
Yeah, I'll just start from the top. So Vitaly has a question that says, since diamond and graphite consist of pure carbon, can properties of these materials and many others predicted only from the CBFE without a crystal structure? Yeah, that's a problem. This is straight up an inherent limitation of a CBFE. We love the CBFE because we're interested in materials discovery, where you don't always know the crystal structure. But on the other hand, our GAN tools are now starting to give us structures and compositions. So it's increasingly looking likely that we will be using more structure information in addition to the CBFE. But that said, you'd be shocked at how good just the CBFE will do. In fact, Jane here, right? Anubhav has a great website called MatBench, which we are big fans of. And we are excited to see that CrabNet, which is, the vast majority of algorithms that people put up there when they're predicting properties for these benchmark data sets, they're using structure and composition. CrabNet only uses composition, and it's on the leaderboard in several categories and right there neck and neck with many of the structural algorithms, the structural features. That's pretty rad. So yeah, to your question, is it gonna get carbon versus graphite wrong? You betcha. But you might be surprised at how good it can do. Next question says, great presentation. What ways for causal interpretation for these generative results have been attempted so far? Oh, that's a really cool. We have not gone into, we're still trying to get it to work. But once you get it to work, trying to understand why it works, looking into interpretability is certainly something we're interested in. More on that coming soon, I guess. I don't have more to say about that right now. We can say a lot about causal interpretation with like our CrabNet, right? Because that has like attention maps. All of a sudden you can see what are elements paying attention to. It gives you interpretability that you never had before. Next one says, thanks for the interesting talk and nice work. In the compute gradient step, when you're generating the vectors on the fly, is there something which ensures that the new vector is chemically feasible? You could. We've tried it both ways. You can constrain it so that it will obey certain ratios and that. Most of the time we don't. We just let it turn it loose. And what's interesting is that it learns based off of seeing lots of examples that certain elemental ratios exist in nature, right? Even though you never told it that aluminum is 3 plus, oxygen is 2 minus, it knows that that should go to a 60-40 ratio because it sees examples like it, which is so cool. Like, this is the power of materials informatics, that it can find those trends, these high-dimensional, complicated, domain-inspired trends, that it's finding those without you explicitly programming them or constraining it. This one says, very interesting talk. Oh, I already did that one. Next one says, the sieve generator is trained to generate sieve cards that are likely to be found close to the convex hull. Does it, or is there a way to account for synthesizability? I've seen synthesizability metrics in organic chemistry. There's a bunch of these things that people come with. I forget the names of them, but everyone I've talked to basically says they're kind of ridiculous, that they don't really work. So if you think I'm wrong about that, tell me all about it, and I would love to learn about it. But I'm not convinced that there are great synthesizability metrics other than stability. If you've made something, actually, I think Materials Project folks have done some of this, so they might be, throwing bricks at their screen right now. But tell me and try and convince me otherwise, and if so, then yeah, let's incorporate those as well. Next one says, any crystal structure can be represented by infinitely many different sieves. Any crystal structure can be represented by infinitely many different sieves. Does this infinite ambiguity make predicting materials properties more challenging? I'm not sure I agree with that first sentence. Any crystal structure can be represented by infinitely many different sieves. I don't know.
I think you can make a supercell, have different bases, like shift the base like the center atom of the basis, all these things. Yeah.
Yeah, I guess I should say we're using the primitive, right? Maybe that answers that. This one says, how can these models, especially GAN and CNNs, or any other ML model, could be used for small data sets around 1,000, 2,000 data points with hundreds of features? So you saw a good example of that with the Discover algorithm. That one, we started giving it only 100 data points, right? So even though CrabNet is an attention model, which are notorious for being data hungry, we gave it a small amount. Granted, we gave it 900 iterations, so it grew to be large, but Bayesian approaches are really good in the limit of small data because it helps you know where to go next, right? Because it gives you uncertainty calculations, right? So CrabNet is not a Bayesian approach. We use aleatoric uncertainty through our neural net architecture, which we stole from Roost, which is another really great model. But I think those approaches that give you uncertainty are really powerful tools in the limit of low data, because if you're going to be gathering more, it tells you where to look essentially. But that said, you say 1,000 to 2,000 data points. That's pretty good for a lot of stuff, and you don't have to use deep learning, right? The same sort of approach could be used with a random forest. Like the Discover algorithm could be worked straight up with a random forest, which would work great, right? Because the chemical uniqueness, none of that changes. It's just your performance proxy changes. This person says, and Vitaly, look forward to seeing you in Liverpool. Amir says, after predicting new materials, there are many experimental parameters involved in synthesizing the materials actually. Yeah, we already talked about that, I think. Then this one is, can natural language processing help improve sieve prediction? We haven't tried it. I think it could. Yeah, we are just starting in NLP. We're not super experts there. If you are, maybe talk to us, and maybe that's something we could work on together. Yeah, we've thought about it. We haven't done it. Says, how composition model in the first few slides distinguish polymorphia? I already talked about that. How have you compared Discover active learning cycle to Bayesian optimization? So we haven't. Sterling, you're on the call. We should do that. We should take this and compare Discover with something like the AXE framework and see how it compares. That's a great suggestion. Yeah, good suggestion. Karen says, thanks for the great talk. Short of the lack of extensive database, can you envision the application of the GAN structure to investigate a property in amorphous materials? Perhaps using short-range atomic clusters for characterization. Yeah, you could totally do that. We've not tried that. I think it's a really cool thing that could definitely be done, though. Yeah, that's an interesting idea. We've been so focused on solving this periodicity problem that, like, yeah, amorphous materials, that's an even harder one, because you still have to worry about things like not overlapping and being sensible, but now you can't even rely on a limited basis, right? So instead you have to start thinking about radial distribution functions or things like that to represent where atoms would end up. But yeah, in principle, you could do it the same way. Yeah, we haven't done it. It's an interesting idea. This one says, how good is the self-checking method for the combination of elements is stable or not? We haven't gone through that, haven't tested it. Are the ML models available for R? Nah, I know R is like, the people like R. We don't use it. We love Python. That's just what we do. So bummer about that. But we do have really great videos that show you how to use it, and tutorials and walkthroughs. You can find all of our stuff on GitHub, on mine or Sterling's or Kai's, or if you can't find it, message me and I will gladly show you our stuff. And even if you're an R aficionado, I think that we can convince you that Python will do the job for you. Amit says, does this tool work for polymeric materials, and how? We haven't explicitly done that because our databases, I think everything you saw me talk about today came from inorganic crystal databases, the PCD, and polymers are just not there. That said, the principles for almost everything I showed you could be applied to polymer materials. Now, what you would probably do differently is how you would featurize it. There are much more sophisticated organic molecule specific packages out there, smile strings and now selfies, and others like that, or fingerprints, or there's tools that we rarely use with inorganic materials but are turning out to be powerful tools to represent materials for polymers. You could use them, but the framework is unchanged, right? Just the tool that you use for the representation changes. And then secondly, say, can we directly get materials properties from 2D X-ray pattern? Sure, you could try it. I doubt it'll do very well, but it'd be cool to try it. I've seen papers where they go from X-ray patterns to structure. In fact, Berkeley people have done this. I think it was Cedar's group did that, or maybe it was you, Jane. I don't remember. So one of y'all did it, right? And I think it did a pretty good job, even for multi-phase materials. Like, it could take a pattern and it could say, these are the different components in it. So it'd be trivial to then say, now that you know the components that are in it, you can now predict properties based off of those with the same tools that I showed you today. So yeah, in principle, you could do it. I doubt it can be awesome, but you could do it. Has there been any material predictions that have industrial application? Tons. 15 years ago, when this really kicked off with, what's his face? I'm forgetting his name. Anyways, the first paper, Materials Informatics, showed up in 05, Krishna Rajan. And, in the not even 20 years, 17 years since then, there was a lot of skepticism early on. But in the last 10 years, there's been so many industry relevant examples that it's no longer like, oh, you have to convince people. The proof is there. Industry is adopting it. Like, the first 3D printable aluminum alloys came out of UCSB and who else? And HRL. That's a great example, right? They couldn't print aluminum alloys because there's problems there. Volatility is the main one, and they figured out how to do it using a machine learning approach. We have partnered with people. A fair bit of my research in my group is sponsored by industry. We have Northrop Grumman as a sponsor. We have Ultradent Products. It's a dental company. There, we have a student making new fillings for your teeth, right, using this approach. So yeah, there are loads of industrial applications at this point. It's becoming pretty standard in industry. This person says, Shyam says, can you talk about the approaches to physically motivate ML compared with methods that embed physical constraints into the operations themselves, like equivariant? I can't. I wish I could. I don't know enough about them, so I don't want to speak out of turn on that. I've read a couple papers on them. They seem really exciting. It's ways essentially to change the network architecture to reflect the underlying physical equations, essentially, like to make it obey. It's making a physics informed model by changing the architecture. I'm just not an expert enough in that area. I hope to be soon. If you are, maybe talk to us. We'd love to learn from you. Danish says, since a lot of materials gain interesting properties due to their defects, vacancies or dopants, right? Can you modify the algorithm to generate different types of? You certainly could, but you need the data. And this is the problem. Like, no one's been able to do this yet because the data does not exist. There is not a big accepted, like, look at MapBench. You won't find on MapBench, which is a great tool, you won't find a repository of dopants, right? That says, here's the benchmark data set everyone should use for predicting things based off of vacancies or dopants or whatever else, because that data is not out there, and it's going to take a paradigm shift to get it, because the amount of data and the buy-in from community is going to be different than what we have right now. So we are certainly working in this area. I've got a friend at Colorado School of Mines, Prashant Garai, who we've been actively working on that with some collaborators in England, David Scanlon and a few others, where we're trying to move in this direction. But The principle would work if you had the data, and we don't have that data. Next says, Gergely says, how about hybrid materials like MOVs, hybrid perovskites? Can you featurize separately the inorganic part of the structure? Sure. I've never done it. You totally could though. Yeah, you could do separate and then you could concatenate, do your prediction based off of the concatenated vectors of the organic versus inorganic. Totally could do that. I'm guessing people have done it. I haven't done it. Last one says, Nirvana says, thanks for this insightful talk. Can we incorporate additive manufacturing process parameters, materials part? You can, and we are with a industry collaborator that will be named soon, I hope. Yeah, this is definitely something they're working on right now with an industry partner. It's not quite ready for prime time yet. We can't quite talk about it, but yep, you can do that. Those are my questions. Anything else I can answer?
Yeah, I think that's it for now. Taylor, that was a heroic effort going through rapid fire questions in a span of 10 or 15 minutes. I think we are over time, so maybe this is a good time to end it. And there will be a recording on the YouTube page for Materials Project. I put a link to that. On materialsproject.org/seminars, we'll also have a page where you can ask further questions later in case another question comes up tomorrow or the next day, and then we can have a community discussion about it. So thank you again, Taylor. Please join me in thanking him, and we will see you at the next seminar. I'll talk to you all later. Yep, bye-bye.
You all, pleasure.